Welcome viewers to the fourth lecture of the series spur and helical gear cutting. In the last lecture, we have discussed about some of the geometric aspects of spur gears, and today we will be continuing with that and also discussing something about helical gears. So, in case of helical gears, let us have a quick look at the depiction. The teeth are slightly inclined with respect to the central axis. So, we have drawn the central axis as a dot and dash line, and the teeth are inclined at a particular angle alpha, which we are calling as the helix angle. Now, you will notice that when we are depicting the helix angle of screw threads and the helix angle of gears, helical gears, they are complementary. Okay. So, let it please be noted that this is the helix angle of helical gears. Let me draw a figure and show you. Suppose these are helices on a screw thread. In that case, we will express the helix angle as this one. And naturally, if it is rising up by P, okay, in that case, if it is a single what do you call it, single start thread, it will be alpha is equal to tan inverse of P by pi d, and therefore, if we take the other angle for helical gears, alpha will be equal to tan inverse pi d by P. This diameter we are taking as d. This one is P. For multiple start threads, P will get replaced by L, lead, okay, and therefore, beta helix angle for helical gears, and this is tan inverse of pi d by L. Okay. So, coming back to our picture, how is the helix angle helical gear different from the spur gear of the same specifications? Let us take such a case. Say this is one helical gear. It is having teeth this way. First question is, what is M? Say M is equal to, once again say 2. What is, and if you remember, M defines the distance between teeth, as we have seen previously. This one distance is defined by M, and this is equal to nothing but, this whole distance is nothing but pi into M. So, here also we will have the same idea. So, mind you, here this distance we have to define this way, perpendicular to these particular gear teeth orientation. This way, this distance is defined by M. Therefore, this distance is larger than this particular distance, which we have to note. Z is equal to, say, once again 100, and say this particular helix angle that we are talking about, say helix angle is equal to beta is equal to 15 degrees. So, in that case, our first question which comes is that, is the outer diameter different? Is the pitch diameter different? For that, I will leave the question to you with a hint. The hint is this: suppose I take a stack of books. Suppose I take a stack of books, some encyclopedias, and I keep it in a shelf. Book 1, book 2, book 3, like that, and say I have filled up a particular stack this way. All these books are volumes of a particular encyclopedia, and they have the same width. Now, someone comes and disturbs this stack, so that they get displaced and they are shifted. What is same between these books? This distance naturally remains the same. Say this is equal to x, this is also equal to x. What is the angle at which it has been disturbed? Say this angle, once again if you remember, this is the angle which is referred to in case of gears, 15 degrees. So, the angle by which it has been inclined is 15 degrees and x remains the same. Can you find out whether from this middle point to the middle point of the last book, whether the shelf will be able to accommodate it or a larger shelf would be required? Middle point to middle point. Once you find out the difference in this particular distance, if there are n number of books, here the distance is equal to n x. Will this be equal to n x once again? Obviously not, this is x. So, it will be slightly more than n x, slightly more than x, and that multiplied by n will be definitely higher. The moment you find out this increase, you have found out the difference in the diameters of helical gears and spur gears. Mind you, we are talking about pitch diameter up till now, pitch diameter. So, let me write down, this is your assignment which we will be solving formally in later lectures, but you can have a quick look yourselves. Find out the pitch diameter of a helical gear with m equal to 2 and z equal to, I do not remember the previous one, 100, and beta equal to 15 degrees. Now comes the interesting part. So, this is the problem that you are going to solve, and the idea that you are going to get is embedded here. I am sure you can do it. Next one is that find the outer diameter as well. Now, here there is a particular catch. Is this one going to affect any increase in distance perpendicular to the plane of the paper? Mind you, all this is wrapped around a particular diameter. That means, we are talking about I am accommodating a certain number of teeth on a circle. I am accommodating the same number of teeth, but inclined where the normal distance between these teeth, they are supposed to remain the same. This is sometimes called as referring to system of normal module, same normal module. So, if this distance is supposed to remain the same, we will have to accommodate these in a larger diameter. The diameter of the helical gear with the same number of teeth, but with a helix angle has to be higher. But this we are coming up to the pitch diameter. Will the outer diameter be found out just by adding one module here and one module there? Remember, the addendum is equal to module. We have moved up to the pitch diameter by this calculation. What about this part? This part should be equal to module. Why should this part change? This is in a direction perpendicular to this particular dimension, which has got affected. If this dimension has got affected, why should it affect a distance perpendicular to it? So, outer diameter or outside diameter should be equal to still pitch diameter plus 2 module. This is what we arrive at. So, please find out outer diameter this way, find out the pitch diameter, find out the root diameter also, and then we will compare our answers in the next lecture. So, with this one, let us take up a few problems which will introduce you to use of gearboxes etc., when we are actually discussing cutting problems. Have a look at this, the actual use of gearboxes in machine tools. First of all, why are we studying this? We are not supposed to become masters of gearbox calculations, no, but this would be required because we will be extensively using gearboxes and gearbox ratios, their calculations etc., in our subsequent lectures. That is why one or two examples will really help. What is this? This is the depiction of a ordinary center lathe. There is a motor, and from there we are leading on to a speed gearbox. Okay, it changes the speed of the spindle. So, the spindle is rotating. You can change the rate of rotation of the spindle by changing the settings of the speed gearbox, and after that a tapping has been taken. That means, power has been taken from the main spindle by a 1:1 speed ratio to a box called F. This is the feed gearbox. Okay. So, we become conversant with the idea that there are two gearboxes on the lathe, and one is called the speed gearbox, which changes the speed of the spindle, and one is called the feed gearbox, which changes the speed of say the feed rod or the lead screw, whichever might be the case. So, in this case we are showing the lead screw, and it is connected to the half nut of pitch 4 millimeters, and that is connected to the carriage, and it is cutting a thread. The question is, in order to cut a single start thread of pitch 1 millimeter, the gear ratio F should be, gear ratio F is equal to output RPM by its input RPM equal to 0.5, 0.25, 0.2 and none of the others. First of all, we have taken up this question from two aspects. One is to understand the positioning of gearboxes, and to understand the way its gear ratio is to be calculated. Please look at this drawing, which I am going to do on the piece of paper, and try to answer these questions. If I have a motor, and then I am claiming that yes, I have a speed gearbox here, from which I am starting the rotating the workpiece. Okay. Now, you will find that in the figure we have taken a tapping from here, and then I am putting another gearbox called feed gearbox, and then I am rotating something. On that I have put a nut, and moving it. Now, first of all, I could have connected it up here. Let's call this point 1 and let's call this point 2. Do you think this would have been better? So, let's have a look. How is location of a gearbox decided on a machine tool? If I had connected it here, in that case, so suppose I do not connect it. So, if we can write if FGB, that means feed gearbox is connected to 1, then what would have happened? Actually, it is connected at 2, if it is connected at 1. In that case, whatever changes you make in the speed gearbox would not be registered, okay, by the feed gearbox. So, suppose you make the speed of this one half of what was previously existing. So, this slows down, say from 100 rpm it comes down to 50 rpm. What happens to this one? This rotates undeterred. It is not affected by any changes because it has taken the tapping of power upstream of speed gearbox. So, even though speed gearbox has slowed down by half of its previous value, this one is undeterred and it rotates at whatever speed it was rotating previously, and this moves at the same speed, and hence the relationship of movement gets disturbed and you will be cutting a different thread, because thread is defined by movement of this one per rotation of the workpiece. Workpiece is moving slower now and you will cut a smaller pitch thread, half the pitch will be cut now. So, it is a problem if you connect it here, and if you are doing something to the speed gearbox, be very alert, because your thread which you are cutting, it will be changed. You will say, I am simply changing the speed because I want to cut faster. No sir, if you make any changes here and you are having the tapping of the speed gearbox here, you are in trouble. So, by logic it has to be here, because whatever changes you are making here should be shared by this line also. Otherwise, their relationship will be disturbed. Wherever you are doing something important, doing something where relational motion is important, you really cannot do this. So, that is why you have to be very alert whenever you are doing something. What are you doing here? You are cutting a thread. How is thread pitch defined? Thread pitch is defined by the linear motion of this one per rotation of this. Here is that relation that we are talking about. So, first thing we notice about location of gearboxes is this: whenever you are relating some motions, always have the bifurcation of power after the gearbox which is defining the motion of the first one. So, that is why we have taken the power tapping here. Change the speed now. This will become faster or slower. This will also become correspondingly faster or slower, proportionally faster or slower. So, there will be no change in the relational movement which was taking place, which defines pitch. So, having understood the reason for putting a gearbox at a particular location, we now go for the calculations. Coming back to this figure, let us have a look at it. In order to cut a single start thread of pitch 1 millimeter, so by the time this spindle rotates once, the carriage should be moving by 1 millimeter. Okay. the gear ratio F should be, that is output RPM by input RPM, equal to these etc. So, let us have a look. The nut is having 4 millimeters pitch. Here there is 1:1 ratio. So, by the time the spindle rotates once, this particular shaft will also rotate once. So, by the time once it passes through F, if this ratio of output RPM by input RPM be say F only. So, this will be 1 into F as the output, 1 into F is the output. So, 1 into F is the rotational rate of this lead screw, and therefore, if pitch is 4 millimeters, the movement of the carriage will be 1 into F into 4, because 1 rotation 4 millimeters, F rotations 1 into F rotations 1 into F into 4 millimeters of movement. So, we have if you come to this page, 1 into F into 4 must be equal to 1 millimeter, because we have started with a consideration that I am rotating. That is why I have written this one every time. I am rotating the spindle by 1 rotation. 1:1 ratio makes the shaft just before the feed gearbox rotate by 1 rotation, multiplied by F, which is the factor output by input RPM of the feed gearbox, and multiplied by 4, because 4 is the pitch of the nut thread. This must be equal to 1 millimeter, that is the requirement. So, F is nothing but 1/4. Okay. F is nothing but 1/4. Let us look at the problem now. Yes, B is the correct answer. Okay. So, we will have lots of applications of this particular thing in our subsequent lectures, where we actually discuss machining of gears. This is just for practice. Another one, slightly different configuration, but this will also help you to understand the application of gearboxes later on. In the CNC feed drive shown, the basic length unit, that is the movement of the table per step of the motor. So, what do we have? We have a CNC system in which there is a stepper motor which rotates in steps to cover one rotation in 200 steps. So, one rotation is 360 degrees and 200 steps are making up that one rotation. Therefore, per step it is moving by 1.8 degrees. So, for that 1.8 degrees movement, we are asking what is the table movement. So, what is given? If you notice, stepper motor 200 steps per revolution is given. Basic length unit is defined and given here, movement of table per step of the motor, 200 steps making up 360 degrees of movement, and gearbox ratio, which is always output RPM by input RPM, that is also given 1/4. Lead screw pitch is given 4 millimeters, double start, mind you, double start. We have been discussing about double start, single start, multiple start. So, here is an actual application. So, let us calculate this and find it out. So, we have stepper, (200 steps) one rotation, one step, 1/200th of a rotation. All right. Therefore, I start with 1/200th of a rotation, multiply it by the gearbox ratio 1/4, multiply it with the lead screw lead lead screw lead is pitch, pitch is let me write down here, pitch into number of starts equal to 1 by 200 into 1/4 into pitch is 4 millimeters and its double start. So, multiplied by 2 equal to 1 by 100, 1 by 100 millimeters. What is 1 by 100 millimeters? The basic length unit, that means the smallest distance, or rather the distance moved per step of the stepper motor. Okay. How much is this? Therefore, this is equal to 0.01 millimeters equal to 10 microns. Okay. So, this way we understand how the location of the gearbox can be decided and how calculations can be done in order to find out the output which a particular gearbox is providing. Okay. If you have a look at, if you have a look at the typical problems that we are going to discuss, I will discuss a very short problem which you can solve yourselves. So, say here we are having a gear connected with another one with this So, let us see what sort of configuration that we are talking about. I might say that here I am providing you 1000 RPM. Okay. These are spur gears. So, they are rotating say this way, this one is rotating that way. Now, this one I wanted to introduce some typical figures. These are two bevel gears which are connected with each other. Bevel gears will transfer power from one axis to another axis, which are generally intersecting, and while transmitting power from one axis to another, these might be intersecting at 90 degrees. So, that when this is rotating this way, this is rotating say this way, etc. And this one is having on the same shaft another gear which is in connection with a rack. So, I wanted to introduce these figures so that you are conversant with this sort of configurations. There might be yet another one where I can have say a motor, shaft is coming out, I put a worm gear here. With the worm gear I put a worm here, with a worm gear I get a configuration like this. I can have a bevel gear here, bevel gear pair, this one is taken on this side. So, this motor is rotating this worm gear. So, this worm is rotating this worm gear. This worm gear is rotating on its own shaft a bevel gear. This bevel gear is rotating this bevel gear. This one is rotating this shaft, this gear, and together with that gear. So, as you can see, bevel gears can be drawn this way. Okay, one bevel gear, another bevel gear. They can be drawn this way. One bevel, another one. Worm and worm gears can be drawn this way. This is the worm, this is the worm gear. They can also be drawn this way. This is the worm and this is the worm gear. Okay. Many times what happens is we include these drawings in a figure and ask a question, and the student in the very beginning is at a loss to understand what has been depicted. So, in this case, now after seeing these, you can easily recognize, yes, this is a worm and this is a worm gear, this is a bevel and its pair, this is a rack and its connecting pinion. That pinion is connected to the bevel gear on the same shaft. That bevel is connected to this bevel is connected to this spur gear pair, and then it is ultimately getting some input of 1000 RPM. So, when we discuss further problems, we will have applications of these figures very frequently. So, with this we come to the end of the fourth lecture. Thank you very much.